He will present himself, but I will still present him a little bit. He's going to talk about smart contracts and how to avoid any pitfalls whilst building them. Our speaker has a little more than 15 years in programming Erlang language, just a little bit over. So a round of applause for that. Come on, guys. I think that's really cool. He's a PhD, but I think he's really eager to speak. So I will let him just jump ahead and present.
It's always nice to get a nice presentation. Can you hear me well? Yes, great. I can hear myself as well, which is really great. I was asked to say something about Sophia, which is the smart contract language of Aeternity. I will not show you a lot of code. I will not show you how to program in Sophia. I will rather have a bit of a discussion, or I will do all the talking, but I will discuss with myself. It's nicer, you get better answers that way. But I will have a bit of a discussion about how we thought when we designed the language. Who am I? As said, I have a little bit over 15 years of Erlang experience. Stumbled upon it by chance, but it's stuck there. I got a PhD in testing and verification of Erlang programs. And about almost 2 years ago now, I got dragged into Eternity and started doing blockchain. It's been an awful ride. No. I had lots of fun. I've learned tons of stuff and had lots of fun. In the beginning, I was doing all sorts of things. I was doing peer-to-peer protocol. I did the Erlang noise implementation, did sync of the blockchain. But in the last year, I've focused more on development of the contract language and of the VM where the contract runs. So when we started designing Sophia for Eternity, the main goal that we wanted to achieve was to make something where it is at least harder to make mistakes. There are lots of blockchain contracts out there, smart contracts, with bugs. People lost money. So we wanted to make sure that, well, if we can, remove the most dangerous constructions. Don't try to do things in an automated fashion. Try to make everything as explicit and obvious as possible. This might lead to that you have to write 10 more characters or one extra line in your contract. But when you're looking at the contract, you will see, if you have the right glasses on, you will see what the contract will do. There will be hopefully no hidden surprises. And that should make it easier for you to write a contract that only does what you expect it to do and nothing extra. And as I said, there has been some costly mistakes. Those who have been in the business probably have heard about a few of those at least. And there was even someone who collected a list of common mistakes. So this DASP, the Decentralized Application Security Project, they made a list. They did this back in 2018. So it's pretty Ethereum-centric because that was the main platform alive at that moment. But it lists and discusses many of those costly common mistakes that were made in smart contracts. And since this presentation is only 20 minutes, let's focus on the top 5 of those costly mistakes. First one, denial of service. What do we mean by that? Well, either that someone malicious takes control of your contract and makes sure that you cannot really run it anymore. They might introduce a data structure which is too large, so you can't process it without hitting the gas limits. You can't pay out because you hit the gas limit. Someone might fool your access control and maybe even kill your contract. This happened to the Parity multisig wallet, for example. Someone took ownership of a subcontract and just killed it, and that's kind of a problem if you can't really use your contracts anymore. In Sophia, well, there is no way to kill a contract. And we have plans for it, but we have talked some more, but there's nothing more that got any further than the idea stage. The idea we have is that you will collect references to your contract. How many are using it? How many will be affected if you kill it? And unless that counter is 0, you can't kill the contract. Of course, you can still make really bad contracts in Sophia. It's a programming language. It's not psychic, so it can't really read your brain and do what you think it would do. There will still be all the possibilities in the world to make mistakes. So if you design it badly, you will still hit these problems. You will run out of gas. You will whatnot. And yeah, we could restrict the language, but then you wouldn't be able to do anything with it. The easiest way to make your contract language not lose tokens is to not allow it to touch tokens. But yeah, that's not the language you want to actually use. So that was number 5. So move on to number 4. They dubbed it unchecked return values for low-level calls. When I tried to understand it, it really means, well, they have a send function where you send tokens. This function may actually fail, but it fails in a very silent way. It returns false. And this is a little example of a stupid withdraw function. The user can withdraw his funds. It requires that he has a balance, and well, then you subtract the balance, and then you subtract it also from the global balance of the contract, and then you try to send the amount. And if this contract for some reason doesn't accept that, well, you have already deducted the balance. This will be written to chain, and the user has effectively lost his funds from this contract. Really a programming mistake. There is a transfer function which will fail in the obvious way. But, well, if I were a programmer, send is half the length of transfer, almost. So of course I would write send. It's much shorter. And I would probably forget to check it as well. So it's a way to make a mistake. Here's the same contract in Sophia. This is the only Sophia bit I will show. We do exactly the same. You check that the user has the balance, and we check also that the address we're paying to is actually payable. And then we actually spend. And if for some reason this doesn't work, if there are no funds, well, it's obviously payable because we checked. If it fails, it will fail completely, and the whole contract will be rolled back to the previous state. And then, of course, in the end, we should notice that now the user has actually withdrawn his amount from this contract. So he can't do it again, but he can do it once, and it will be all safe. And if it fails, it will fail completely. And yeah, he still probably has a problem, but then he has at least a fighting chance to fix it. So yeah, in Sophia, the spend function will fail with an exception, and everything will roll back. That was number 4. So moving on to number 3. All sorts of arithmetic issues, mainly overflowing and underflowing integers. And by making overflow or underflow errors, you will trick the contract logic into doing something that you didn't intend it to do. Again, a small solidity example. If you send it a large enough amount, the balance check will underflow, and it will still be successful, and you can withdraw more money than you actually had from the beginning. Not really what you anticipated, so you would have to add some extra checks. In Sophia, on the other hand, or in Aeternity, Sophia contracts are backed by 2 different virtual machines. We have the AEVM, which is the old one, and we have Fate, which Eric will say something about really soon, which is the new one. In the old one, in AEVM, we decided to do these arithmetic checks built in, so you can't get around them. You always have them. So if you have an integer that overflows or underflows, you will automatically get an exception, and your contract will abort. In Fate, on the other hand, we have solved it much more nicely, there are no bounds on integers. Integers are infinite in theory. In practice, you will pay gas for the size of the integer, and the size or the cost of the integer will grow exponentially when it gets larger. So you shouldn't possibly, or you probably shouldn't use too large an integer, but you don't at least have to care about overflow or underflow, which saves you from thinking about one extra thing as a programmer, which means you can focus your energy on actually not making other mistakes. You don't have to worry about those mistakes. That was number 3. Over to number 2, which is access control. Mainly, as I understood it from Solidity space, you have problems where you can rerun the initialize function, or where you can bypass some control flows by doing some stupid, almost reckless usage of delegate call, where you call another contract but stays in your environment, so that contract can do arbitrary changes to your state. And this was manifested by 2 different hacks or bugs in the parity multisig contract. In Sophia, well, firstly, you can't re-evaluate the init function. We are actually removing it, so it's not actually even in the contract, so you can't call it. Secondly, we don't have delegate call, so you can't, even if you try to, you can't do something like that. If you call another contract, that contract has its own state. It may change that state freely, but it can't change your state. So your state, you're handling. If you're calling another contract, you switch over to another state, and it can't touch you. And thirdly, all the places where your state is updated, they are tagged. You have to explicitly call the put function to say that now I want to update the state. This makes a great difference when you're trying to look at the contract, review it for security or for any other aspect. It's immediately obvious where the state changes. It helps a lot. Still, as for the number 5, I think, locking this down completely so that you can't make any mistakes, the obvious thing would be to make the state read-only, which would be kind of a problem because you have a state because you want to actually save something in it and occasionally update it. So we give you the gun. You can safely point it at your foot and you can shoot it and it will hurt. But we give you at least a little bit of a smaller gun, but it will still hurt, so it won't save you completely. That was number 2. Moving on to number 1, reentrancy. This is also a problem I've understood. It's also known as the race to empty, or recursive call vulnerability, or call to the unknown. And the problem is, in Solidity and other languages, you are allowed to, from within a contract, to call another contract. That contract may go away, maybe call a third contract, and then that contract is allowed to call back into your state and possibly get there in a place in the logic where you don't expect it. Typically, if you are withdrawing funds, if you spend the funds to the other contract first without updating your local state, they can then call back and do another withdrawal, and they can withdraw money until the contract is actually empty rather than their individual funds are empty. This happened to the DAO and many more places. Small mistake, but it makes it really hard to reason about. And so we decided, well, that sounds really stupid. Why do we allow that at all? So we went away and said, yes, well, if you try to call back into a contract, well, we will fail. If the VM will throw you an reentrant call exception, and you will just get stuck. All the things that happen will roll back, and you will not risk ending up in a state where you didn't anticipate. And also, there are no default fallback functions. If you want to call something in Sophia, you have to call a function, it has a name, it has a type. There's no chance to just call something and then you will end up in some unknown piece of code somewhere. Which should help you keep safe. So if we are to summarize this, well, I'd say that Sophia actually does something. Maybe not all of it, but something for all 5 of those, which is pretty good. That's 100% success rate in the design. But, and yeah, this is the a little bit sad part. Does that mean that you can't write bad contracts and that you can't make expensive mistakes? You should know the answer by now. No. If you have a bad day at the office, or your colleagues have a bad day at the office when they review your code, you can still make mistakes. It's a programming language. It's, you can write anything. If you want to give away your funds, you can do it. But what we really aimed to do was to at least force you to do new, novel mistakes, not repeat the old ones. So we tried to learn a little bit from history. We went away and designed something, and we hope it's a little bit better than what was there before. And my final piece of advice: let's try not to be stupid. That will save you a little bit at least. Thank you.
Thank you. You know what? Let's have a quick question, because it's like a very touchy subject, and I'm sure people have questions. So let's have one. Let me pick between you. Sorry, I didn't see whose hands was first, but I'm gonna pick him because I think I saw his hands first. Sorry.
So if I'm writing a contract and I have a for loop, and within that loop I'm calling another contract.
There are no for loops in Sophia. It's functional.
Oh, crap.
That's a great question. That's a great question. I love it. No, go on. All right, let's have one more because that was quick.
Thanks, great presentation.
Do the same.
No,
No.
I just want to say thanks, great presentation. Why did you decide to? One of the problems we are addressing, yes, you decided to throw in exceptions.
Yeah, call that what you want, but the execution will stop. Yes.
Exactly. So another approach to it would be to force a compiler to check if you check the return values. So instead of throwing an exception and then have a problem up in the stack.
Yeah, we locally check. We have the stateful checking of our local contract, local things. But once you cross a contract boundary, it's impossible for the compiler to know. You might not even have the code of that second contract, so the compiler can't really check.
Okay, so then it's an issue on the, let's say, compiler stack.
You could make it some sort of whole program analysis, but that would be the next step of tooling here, I think, that you collect all the pieces and all the contracts, and then you can analyze it.
Thanks.
Right, thank you, guys. That's it, because I'm gonna go with the next speaker. So round of applause again.